Hello there, organickers. We've been working on nucleophilic substitution reactions, and this is a very characteristic reaction of alkyl halides. In a substitution reaction, you may recall from an earlier video that one group, and in this instance X, is going to be replaced by a second group Y. So basically Y displaces X. This is in general a substitution reaction, but more specifically, in the case of alkyl halides, these are nucleophilic substitution reactions. Or in other words, the alkyl halide is being attacked by a nucleophile. In this example you're looking at on the screen, the nucleophile is Y. So why do alkyl halides behave this way? Well, let's look a little bit more closely at alkyl halides. You may recall that carbons and halogens have very different electronegativities. As a result, the carbon-halogen bond is polarized. Carbon is going to be at the positive end of the dipole, whereas your halogen, which is more electronegative than carbon, will be at the negative end of the dipole. A nucleophile, remember, is a species that has a lone pair of electrons that it's willing to share, and the nucleophile will use that pair of electrons to attack the positively charged carbon. Let's look specifically at some methyl halides. We have methyl chloride, methyl bromide, and methyl iodide. And remember that these are our electron density maps, and the red areas are meant to show regions of high electron density. The blue areas are meant to show regions of low electron density. So you can see from the electron density maps that the halogens all have partial negative charges. As we go from chlorine to bromine to iodide, we are going down the periodic table, and we are decreasing in electronegativity. We're also increasing in size. Now, I'm not showing you methyl fluoride here, and the reason is that even though the carbon-fluoride bond is highly polarized, the fluoride anion is considered to be a very poor leaving group and doesn't work very well in nucleophilic substitution reactions. I also want to point out to you that we are going down in the periodic table as we go from chlorine to bromine to iodine and increasing in size. Now, you may remember from our chapter on acidity, as an atom increases its size, it is more able to accommodate a negative charge. This is going to be an important factor when we consider the rates of nucleophilic substitutions a little bit later on. Let's look a little bit at some of the terminology that we apply to nucleophilic substitution reactions. First, we have our nucleophile, Nu-, attacking our alkyl halide, which is our substrate. It is displacing the halogen, and we call the halide anion the leaving group. This is just a simple example of a nucleophilic substitution reaction. In this reaction, we have iodide taking the place of bromide. I-, iodide anion, is our nucleophile. Br- is our leaving group. Now, you'll see later on that iodide anion is actually a better leaving group than Br-, and this reaction would be better represented with an equilibrium arrow, and other things being equal, the equilibrium for this reaction should lie to the left because I- is a better leaving group than Br-. In this instance, our byproduct, sodium bromide, is insoluble in acetone. Acetone is the solvent that we run this reaction in. Our sodium bromide is going to precipitate out of solution, and that is going to draw the equilibrium to the right. The name of this reaction is the Finkelstein reaction. Here's a second example. In particular, we call this reaction a solvolysis reaction. In other words, we're replacing Cl- with water. We have the solvolysis of isopropyl chloride in water. Water displaces chloride anion. Cl- is our leaving group. Water is our nucleophile. We end up with an intermediate that would be an oxonium ion, and the proton is taken away from the oxonium ion by another molecule of water. These reactions find wide applications in synthesis because we can use many different types of nucleophiles to produce a wide variety of products. For instance, You've already seen the use of halide anions as nucleophiles. That will give us a different alkyl halide. The use of OH- will give us an alcohol. OR- will give us an ether. CN- gives us a group of compounds called nitriles. If we use a carboxylate anion, our product will be an ester. If we use an acetylide anion, our product will be an alkyne. Remember that we could pull a proton off of acetylene, or a terminal triple bond, to give us an anion, and these are very strong bases. That makes them very good nucleophiles as well. We can use a thiolate anion to give us a thiol. So in all of these reactions, we're showing in the boxes our nucleophile, which has replaced our halide anion. Also, you'll notice that in all of these examples, our nucleophiles are negatively charged. Nucleophile doesn't necessarily have to be negatively charged. It only has to have a lone pair of electrons that it's willing to share. So here we see a few examples of nucleophiles that are neutral, yet they have a lone pair of electrons, and they can still act like nucleophiles. In general, we have to have a second step in this process, which is the deprotonation of the intermediate product. In the case of water acting as the nucleophile, that intermediate is an oxonium ion. If ammonia or an amine was our nucleophile, that product would be an ammonium ion. You may recall from a previous video that there are two different types of nucleophilic substitution reactions that are characterized by different kinetics. In the first type, we called SN2, the rate of this reaction depends on the concentration of the substrate, the alkyl halide, and on the concentration of the nucleophile. We say the SN2 reaction is bimolecular. In the second type, we call that SN1, and the rate of that reaction depends only on the concentration of the alkyl halide. We say that this reaction is unimolecular. Let's look at the mechanisms for these two different reactions. And let's begin with SN2. Remember that SN2 is second order. We have to have two species come together in order for our reaction to take place. This reaction is bimolecular. Here we have our starting alkyl halide, and I just want to remind you that we have a partial positive charge on the carbon, a partial negative charge on the bromine. Our nucleophile in this case is hydroxide anion, and keep an eye on the energy profile in the upper right corner. The nucleophile approaches our partially positively charged carbon, and it begins to push away Br-. Also note that our nucleophile approaches from the opposite direction of the carbon-bromine bond. We have the formation of a transition state. Remember that that's the highest point on our energy profile, in which we have partial bond breaking and partial bond making taking place at the same time. Br- begins to leave. We have a new bond formed between our nucleophile and our partially positively charged carbon. And now our reaction is done. But I want you to notice that we have inverted that carbon because of the direction of approach of the nucleophile. So here's our complete energy profile with our starting materials on the left, products on the right, our transition state at the top of our potential energy hill. And remember what our transition state looks like. We have a partial bond between carbon and bromine, or our leaving group, and a partial bond between the nucleophile, in this case OH-, and the carbon. Well, what are the stereochemical consequences of this type of reaction mechanism? The old bond is broken simultaneously with the formation of the new bond. The outcome of this reaction is very well defined, in that the stereochemistry is inverted. Have you ever been outside in a strong rainstorm and had an umbrella turn inside out? You can think of it as something like the inversion of an umbrella. So if we started with S2-bromobutane and attack that with our nucleophile OH-, our product is going to be R2-butanol because we invert that tetrahedral stereocenter. In our last video, you may recall that we said that the most important factor that affects the type of mechanism that these alkyl halides go through in a nucleophilic substitution is the structure of the alkyl halide, with the SN2 reactions being fastest for the methyl halides and slowest for the tertiary halides. As the carbon that is being attacked gets more substituted, it's more difficult for the nucleophile to approach. There's just less room, and we call that steric hindrance. So if we consider our methyl group, we can see the carbon that the nucleophile is going to attack, and so can the nucleophile. Here we have a primary alkyl halide, and we can still see that carbon. With our secondary alkyl halide, the carbon is starting to be blocked a little bit, but we can still see it, and so can the nucleophile. But by the time we get to a tertiary alkyl halide, we can no longer see that partially positively charged carbon, and neither can the nucleophile. Other factors that affect the rate of the SN2 reaction are the leaving group. In terms of leaving group ability, iodide is better than bromide, is better than chloride, and we almost never see fluoride anion acting as a leaving group. The lower the basicity, the better the leaving group. If you think back to when we talked about acids and bases, you may recall that we said HI is a stronger acid than HBr, which in turn is stronger than HCl, which in turn is stronger than hydrogen fluoride. A good leaving group is the conjugate base of a strong acid, or you can say that a good leaving group is a weak base. What about the nucleophile? The nucleophile, you may recall, is also involved in the rate-determining step. So what makes a good nucleophile? In general, a good nucleophile is a good base. That's not always the case, and we will discuss the situations where it is not the case. Most of the time, a negatively charged nucleophile will be stronger than a neutral nucleophile. So here we have OH minus being stronger than water, and methoxide stronger than methanol. So the better the base in general, the better the nucleophile. Also, as we go across the periodic table and our atoms that bear the negative charge become more electronegative, nucleophilicity decreases. N minus is a stronger nucleophile than O minus, which is in turn stronger than F minus. So we can say that a strong base is a good nucleophile, or the conjugate base of a weak acid is a good nucleophile.